We're going to talk about the difference between digital and analog. This gets thrown around a lot. Usually people spend a lot of time explaining what digital is, but they don't explain what analog is, so the contrast doesn't come across really well. Let's look at what analog means. An analog is basically saying this is like that. So that is an analog of this. An example. You get a car, it's going down the road. Phenomenal artwork, I know. And the wheels are turning around and around and around. On the dashboard is your steering wheel. And here is your miles per hour. As this moves, the way it moves is like, or is an analog of, how the wheels are turning, or how fast you're moving. That's an analog. Specifically, what an analog is in terms of devices is a device where the data displayed is real-time representation of something else. And you know this, when you hit the gas, the needle moves because it's a real-time representation of what's actually happening with the wheels. The meter is an analog of the actual physical condition of the wheel. So, what is digital? Well, the key is in this real time. Digital isn't like that. You can make it look like it is, but it's not. What happens with analog, when you're looking at a dial, for example, there's an analog dial. You can watch it over time, and you can look at whatever quantity, and you can observe it. If you are accelerating out away from the stop sign, and you're a lead-foot driver, you'll accelerate really quickly. Teenagers, this is what they shoot for. I am more like this. So, what happens is, in analog, this is the real world of what's happening in terms of, say, the tires turning in our case, right? And the meter represents continuously, split second by split second, what's actually occurring in the real world. Digital is not like that. First of all, digital comes from digit. What does that mean? That means, well, when you're counting 1, 2, 3, 4, 5, these are, of course, they're numbers, but they represent specific quantities. There's one of a thing, there's two of a thing, there's three of a thing. Let's go back to our illustration here of miles per hour. It could be 80, 81, 82. I do like to drive fast. But the point is, at any split second, you could look at that and you might be at exactly 80 miles an hour. Well, you look at it a little while later and you're at 81, but the fact is, time occurred and you moved up towards 81. You didn't suddenly go from 80 to 81 like that, instantly. Digital can't handle that. Digital can only handle what are called discrete values, meaning they are singular, they are unique, they are the only thing, and they are not in between that unique value and another adjacent value. There is no between. There is only 1 and then 2, and then 2 and then 3. There are only these values available. In fact, in a computer, as you already know, the only things it can actually work with is there's nothing or there's 1. That's all it can work with. Those are the only digits it works with. So, how do we get computers to do things like show us speed, rates of change, things that actually happen over time? Here's how. Let's say you've got that wheel and it's turning. And over here you have a computer. And it's got a little device that can look at that, and every second it says, what's the speed? At second 1, what's the speed? At second 2, what's the speed? At second 3, what's the speed? It's going to get a singular snapshot of time. And it may very well be that the speed here is 10. The speed here is 10.5. The speed here is 11 miles per hour. The computer didn't observe the transition through time from 10 to 10.5. That happened when it wasn't looking at the wheel. So the computer can only get this one discrete value. It doesn't know anything about what's in between it and the next discrete value. You make the computer read what's happening in the physical universe at exact, precise intervals. And it takes what it finds out about the physical universe and converts it to a discrete, exact number. It's exactly 10. It's exactly 10.5. It's exactly 11. It's not somewhere in between and able to be watched in the in-between process. So digital means you're dealing with digits, discrete, precise, exact intervals or quantities. So, another example of how this could be, how it could be used, and why sometimes analog is good and sometimes digital is good. Let's say you have a tank filled with water. You have a device on the side of it that lets you see the level in the water. This right here might mean 50 gallons. This might mean 25, and this might mean 75 gallons. You want a device to see the level. Well, if you're looking at analog, you'd have the water could come in this little tube, and it would be in this tube at the same level it was in the tank. And you have a little floating device in here that was able to move up and down on a track, and something connected to it could check how much of electricity comes off of it. Great spelling, right? So you send electricity through the bottom of this channel and then out the top, and because of the position changing of this little floater, the amount of electricity coming out changes. Good. That's your signal. And you could watch this and watch it change in real time. You can watch it rise. You can watch it fall. That's analog. You could even take this and you could put it on a meter where it said 75 gallons, 50 gallons, 25 gallons, and 0, empty. And you can watch it change over time as you emptied out or filled up the tank. That's analog, because the position of the meter is like the actual level. How would you make this digital? Well, take this electric signal. And you feed this signal, it was called an analog to digital converter. It's a piece of electronic equipment. And what it does is, at regular, precise intervals, over time, it does something. 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. It's actually a lot faster than that, but this is for illustration. Every second, exactly on the second, it checks the amount of electricity. So if you were looking at what happened in this as you filled it up, you would see the water level slowly increasing. This would be time. This would be water level. But what the computer here is doing, this analog to digital converter, is it's checking at this exact moment, and then 1 second later at that exact moment, and then 1 second later that exact moment, to see what level is indicated. and its output would be something like 50, and then a second later, 51, and a second later, 52, and a second later, 53, in terms of gallons. This is not an analog anymore. This isn't that the signal coming out is exactly like what this is doing, because this is increasing, the water level is increasing at a rate over time that you can watch happen. And there's no set jumps, it just is continually changing. To convert it to digits requires an analog to digital converter. And then if you actually wanted to take this and display it on a meter, well, now you got a problem. You would require actually a separate thing called a digital to analog converter to turn it right back. But you're not usually doing something like this because you're not using these meters. What you'd instead be doing is taking these now digital signals, putting them into another computer, and maybe storing them into a permanent memory. So you can recall at a later time what the exact level was of this tank at an exact point in time. That's analog versus digital. Now, let's have a lot of fun and dive deep inside a computer. Switching gears, we're going to talk about transistors and central processing units and all the hardware inside the computer. What it is, how it works, that sort of thing. And the segue here kind of makes sense because we just talked about digital. We talked about the fact that a computer doesn't understand if something is 0 and then suddenly is 1. It doesn't understand the transition from here to here, any gradient states in between. It just knows something is not there and something's there. That's all it can deal with. And it also knows that if there's 50 of something at one point, and then a split second later, there's 53 of them, it only knows those two things. It doesn't know anything about what happened in between. Good. So, inside a computer, what we need a computer to do is operate on very, very simple logic. And that logic is something is either on or it's off. It's yes or it's no. It's hot or it's cold. Silly song, sorry. So, how do you do that? You choose two digits, 1 and 0. What it actually means inside the computer is this. It means 5 volts of electricity is present, or 0 volts of electricity is present. That's it. By the way, for a very simplistic idea of how electricity works, you can kind of think of a battery, which we've all seen before, with a positive and negative. The best analogy, the best analog, like this is like that. The best analogy I've ever seen for this is to think of the battery as like a big giant pump, where a pipe comes into the pump, and the pump can accelerate and push out water. There's a big tank of water into that pump, and the pump pushes it out. It's an energy source. The flow of the water through the pipes does work and is also analogous to electricity. Water flowing equals work done. Water flowing equals electricity for the purposes of analogy. So what does this mean? It means there's a certain degree of flow, a certain amount of potential work that can be done called 5 volts. So, why 5 volts? I don't know. It's a really small voltage. It's easy to build something that can produce that amount of voltage. If they made it 110 volts, the power supply needed to be able to run a computer would have to be really, really strong. It's a separate thing, but it's kind of interesting. So, inside a computer, 1 just means at any specific point in that computer, that 5 volts is present. 0 means that there's no voltage present. It's that simple. So now you have a machine that you can control states of existence, conditions, by applying 5 volts somewhere or removing 5 volts from somewhere. How do you do that? You do that with a really, really cool thing called a transistor. A transistor is a special device for allowing or not allowing electricity to flow. How does it do that? Well, let's say you have this little device called the transistor, and it's got 5 volts of electricity coming in one side on a wire, and it's got a wire coming out the other side. You're looking to find out, can I or can I not get 5 volts there? And you can base a lot of decisions on that. For example, if there's a 1 there, if there's 5 volts there, it could mean, yes, I do want to print my document. Or no, I don't want to print my document. It could mean, yes, the person's actually entered the correct password. No, they haven't. Yes, no, on, off, that thing. So how do you control that? Well, this little device is almost magical. It's got a way, by bumping a very small amount of electricity at a separate piece of it, to allow or not allow electricity to flow. It's a gate. Open it, electricity flows. Close it, electricity doesn't flow. That's all it is. How do you make something like that? Well, it's fun. You take a special metal called a semiconductor. Semi means half. Half the time it conducts electricity, half the time it doesn't. How do you control when it does or when it doesn't? By the way, it's not half. It just means that it doesn't have to conduct, and you control whether it does or doesn't. How do you do that? Well, here's a very simplified diagram or description of a transistor. You have a certain kind of material right here, and then the exact same kind of material right over here, and one that's different in between. And they're all physically assembled together. You have a wire going in, and that wire coming in has 5 volts of electricity. You have a wire going out, and it has, well, we're going to decide what it has. Whether it has 5 volts or 0 volts. Whether it has a 1 or a 0. Whether it has a yes or a no, essentially. But physically, in the real world, what we really care about is, does this device allow the electricity to pass, meaning there's 5 volts there, or does it stop it, meaning there's 0 volts there? The way you do that is by taking this middle piece of material and changing its characteristics so now it's like the ones on either end. Electricity flows. There's 5 volts here. Now you make it change back and it stops electricity flow. How do you do that? Well, the simple version, again, very simplified. The guys at Intel would slap me if I was this simple about it in front of them. This is a special material, mainly from a material called silicon. Silicon is like, it's a mineral, mainly the main ingredient is sand. But you can take sand, for example, and bake it, make it very pure, and then you can do special things to it. You can add other metals to it that change its properties. And one of the things you can do is add a metal to it that means that if you apply a tiny amount of, like, say, 1 volt of electricity to it, it'll warm up and it'll change characteristics to allow electricity to flow. And then when you remove that and it cools down slightly, now it changes back to its first condition, its first state, and it no longer allows electricity to flow. That is what makes computers possible. That's all there is. Because all you really need for a computer, for a digital machine to work, is for it to be able to differentiate between one of 2 states. That's all you need. A yes or a no, a 1 or a 0, a plus 5 volts or a 0 volts, and that's how you accomplish it. That's what a transistor is. So, what do you do with that? How do you go from, oh, that's great, so electricity can go in, and it may or may not come out, and I get to decide. Where do you go with that? What do you do with it? How does that make a computer work? Well, the reason why is because of this thing called a central processing unit. A computer only needs a few things. Basically, it needs a brain to decide what to do. and it needs a way to put input into the brain and a way for it to output things. Most common input devices we're all used to are keyboards, mice. Output devices we're used to are displays, also called monitors. But there's lots of others. And the brain also needs something. It needs memory. It needs a place to put data that it's not using at the moment, but may need later on. That's a computer. So, what is it in physical terms? Well, the brain is a central processing unit. A CPU. A central processing unit is a tiny, tiny, tiny machine. And it's designed to be able to take data in, decide what to do with it, and either then store things in its memory and or output certain things. The cool thing about how this works is that it only does one thing at a time. Now again, the Intel guys would slap me for that, because they've got very, very complex central processing units that can actually do two actions at the same time. But when it really comes down to it, a computer can only really do one thing at a time. And what do I mean? What do I mean by at a time? It means that you have something that every so often, an exact regular time interval, we're going to say every second, although computers operate about 1 billion times faster than this. But every second it goes, do the next thing, do the next thing, do the next thing, every single second. And again, it's actually about 1 billion times every second, but it's exact, precise intervals of time. In between those time periods, the computer's doing nothing. It's waiting. What do I do next? Okay, go? All right, good. All right, I did what you told me to. All right, go? Okay, good. I did what you told me to. That's how it works. You could actually, if you could mock it up, think of a giant physical mechanical machine where you would actually have a series of instructions. Let's see, make that better. You have instruction 1, instruction 2, instruction 3, and they could be physical, actual things that when they went into the machine would cause it to do a precise, exact activity. And you could shove one into the computer, into the machine, and then wait a second while it was doing it, and then shove the next one in, and then wait a second, and then shove the next one in. That's how computers work. They have a series of instructions that are put into them, and they do the first one, and then the second one, and then the third, and then the fourth. And when it all comes down to it, there's really maybe only a dozen basic things it can do. It can do things like do a math operation, plus, minus, add, divide, subtract, multiply, right? It can store something in memory. It can retrieve something from memory. It can send some data out. These are the only things it can do. There's not much it's going to do, but it can do it billions of times a second, and it can do it with a lot of complexity layered on top of it. But the actual central processing unit really only has a dozen, 2 dozen basic actions it can do. And out of all those basic actions, everything you can use a modern computer for is built. So, a little more data here. I said that at regular intervals, every second, every second, every second, it does something. Why? Because of a device called a clock. A clock is a regular, meaning operating at exact intervals, never failing, commander. Actually, initiator is the right thing. It initiates the next action. There's a tiny little wire going into the central processing unit. And there is literally a device, there's a clock, not like the big clocks you're thinking of. They're tiny, tiny, tiny devices that will input an electrical signal. It's usually 5 volts. And then a split second later, input that signal. And a split second later, input that signal. Split second over and over. And every single time it hits the central processing unit, it says, okay, what's the next thing I have to do? Well, how does it do that? On this central processing unit board, will be a tiny, tiny chip, a tiny piece of memory. And all it is transistors. They remember whether they're equal to 1 or 0. They remember whether they actually have 5 volts on the output or 0 volts on the output. So there's all this memory in here. And one of these little pieces of memory, its job is to store in the very next instruction to be run. And so the clock signal comes in, the computer says, hey, what's my next instruction to be run? This is an instruction register, by the way. A register meaning a list of items. So it goes to the instruction register and says, what's the next thing I got to do? Let's say it's retrieve something from an exact memory location. So it's got this huge bank of memory. Every single box of memory in here is labeled 0001, 0010, 0011. Like every single location in there has a number to identify it. So this instruction could say, go to memory location 3 and get the value in there. So it goes to memory location 3, and the value in here might be 1110. Okay, good. It takes that and brings it into the central processing unit to do something with. That something is probably your second instruction. Maybe it's going to add it. Well, add it to what? Well, the third instruction says, go to memory location 4 and get what you're going to add to. And it pulls that in. And the next instruction could be, do the actual add. And the next one could be, store the result in memory location 5. And then you'd have it. I'm not doing binary math right now, sorry. That's what the central processing unit's job is. It's actually really simple. At regular intervals determined by a clock, it sees what its next instruction is, it executes that instruction, and then it waits for that signal again. The moment that signal comes in again, it goes to the next instruction. Where do those instructions come from? You, programmers. At the end of the day, what you're doing when you write your program is you're actually setting in motion the millions of instructions in an exact order that will be fed into the central processing unit and executed one at a time that at the end of the day ends up with your program working. But that's all that really happened. This simple machine has a place to look for an instruction, it gets the instruction, it does it, it waits, when it's told to act again, it gets the next instruction, and that's all that happens. So, a couple other elements of this. What's a hard drive? Let's go back in time a little bit. We talked about this CPU, and it needed to store things. It needs a memory. A long time ago, the actual memory, the way it would store things, is we'd actually have these thick paper cards, and they would have rows on them. And the rows would literally have holes punched or not punched or not punched, based on whether you wanted to store a 1 or 0, a 1 or 0. You can agree on whatever convention you want, but typically, if there was a hole, it meant that there was a 1. How were these read? It's the coolest little thing. You'd have a device with a little slot in it. The card would go in, and of course these rows are all separated by exact, precise distances, and some machine would feed this in one row at a time. When it came in, there'd be a little machine that would shove a pin down, actually several of them all in a row, all along here. If a pin encountered a hole, it would go all the way through, and it would make contact with a little bit of metal down here, allowing electricity to flow all the way through, meaning 5 volts got passed, meaning a 1, meaning yes. If it encountered a place where a hole wasn't cut, the pin wouldn't be able to go through, it wouldn't hit the metal, and so that would have a 0. That's really all there is to it. To take it back to when these were much more physically observable as machines, that's how a computer would work. These were called punch cards. And they were used primarily from about the 1950s through, at the absolute latest, the 80s, but even then they were dwindling. Well, what did they do with them instead? how do you store these ones and zeros that you want to input into a computer? Some of you may have heard of a thing called a Walkman. A Sony Walkman, it is a portable tape player. Not CDs, not MP3s, not whatever you're listening to if you listen to this in the future. But an actual physical cassette, a small plastic box that had 2 reels in it. And wrapped around the wheels would be magnetic tape. Magnetic tape is really awesome. It's a very, very thin material where at exact precise intervals all the way along it, you can either align these little teeny metal particles all in one direction or not, randomized. If they're all in one direction, that's a 1. If they're not, it's a 0. And so you can lay these out, bang, 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 in exact order, precise intervals between them. Exact intervals had to be the same every time. And you therefore could take this magnetic tape and store digital data on it. And then you'd need a machine that could then go and read it. And if all of the metals were aligned in one direction, detect that because current could flow through this section. And if it didn't, well, that's a 0. You've now gone away from the punch cards to a magnetic medium that is capable of storing a lot more data, and you can move to specific spots on it a lot more easily, and it moves a lot faster. Good, so that is a tape drive. All right, those were in use a lot too. Tape drives, well, they're still in use, by the way, commonly for things like backup of large amounts of data, and they're big giant cassettes sometimes too. Those of you who are as old as I am will remember that when they got their first computers, it was small cassettes, the ones that are about yay big, that you could actually store data on. But that's way back in the olden days. So, again, what's a hard drive? All right, so you get this idea of being able to store data magnetically by either aligning metal particles or not aligning metal particles. So, what if you had a big round disk, and at a very small level that you couldn't really see with the naked eye, it was actually organized into rings. And what if every single one of those rings was divided into little teeny sections? And every single one of those sections could either have a magnetic 1 or 0. The particles were aligned in one direction or they weren't. That would be a hard disk. You physically pick it up like a record, right? If you don't know what a record is, I'm sorry. So here you have ones and zeros stored on it, and all you would need is some little device, an arm, would come out on an arm and rotate over here, and you spin this wheel, this disk, and as it goes over, actually as each spot passes under it, it can tell, is that spot a 1 or a 0 or a 0 or a 1 or a 1? And now you can input that into your computer. That's a hard disk. Now, a hard disk drive is so named because you'd have a bunch of these disks all stacked on one another. And you'd have this arm that could go in and read the data, could actually move up and down the track on the outside of the container and move to whichever one of the disks it wants to. You don't have to have multiple disks. There are plenty of drives that actually only have one, but most of them have more than one. That's a hard disk drive. Now let's look at a concept called solid state. This can mean a few different things. Back during that period when computers used those punch cards, and even before, they actually didn't have a thing called the transistor. Instead, where you would have a condition where you really needed to basically have a device which would bring in voltage and then decide whether or not voltage would come out the other end of it, essentially it would act as a gate. When you needed that, they had to have these very, very large devices that consumed a lot of electricity. They were called vacuum tubes. And a vacuum tube would have part of it that could collect the output voltage, and part of it could have voltage coming in, and then a separate thing that they called the gate that could say, let the electricity pass or don't let it pass. And it would have to arc through air, because these were glass-contained tubes. This electricity would have to go through this space. Well, I said it would have to go through air. It wouldn't go through air, because electricity going through air does bad things. We've all seen it. It's called lightning. And it burns tiny particles in the air, and it's not a good thing. What if there were no air inside that glass? The electricity can move a lot more quickly, and it wouldn't burn up things inside there. So they seal these things off, and with a special device, they suck all the air out of them. They have a vacuum in them. Literally, that means if you were to break one, air would suck into it, because there's no air inside there. Those were called vacuum tubes. Many of you have heard that term. All it was a way to solve this. How do I control whether or not electricity is passed to an output? Now, even though this doesn't have physical moving parts, when they moved away from this to the transistor, that tiny, tiny, tiny device, like they're very small, composed of one type of material and another one. When they moved away from vacuum tubes into these, they called these solid state electronics. What the reason was, I don't know, I wasn't there. But that's the original meaning for solid state. It means, as opposed to earlier technologies for accomplishing the transmission of signals. This is a signal coming in, this is a signal coming out, you're transmitting a signal. Good, so that's solid state in its original definition. It's come to mean a few different things over the years though. Many of you have these little things, these little memory devices called thumb drives, flash drives, memory sticks, whatever you're gonna call them, right? So here's what's cool about that. Those are also called solid state memory. In fact, many of you heard of a thing called a solid state drive, as opposed to a hard disk drive. What does that mean? Well, before, we'd have disk after disk after disk, all in an enclosure and an arm that came through. That arm would move. The disk would move. That's not a solid state. Instead, you replace that with a tiny little circuit board, and on it are many, 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 many memory chips. And remember, all these memory chips have on them is just transistors. Lots and lots and lots of tiny little transistors. They can store ones and zeros. And that's what's on there. And that's all that's inside the little thumb drives that you have, is many of these chips. They can store many, 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 many ones and zeros. They're called solid state because nothing's moving inside there. Here, there's something moving. The disks and the arm move. So, that's a thumb drive. What's a solid state drive? Well, this is different. Subtly. It's the same technology, but it's a matter of terminology. So, when you have a computer, personal computer, and you have external storage, memory, this is your hard disk drive for many, many, many years. They call it a hard drive. Well, if you replace it with something that actually uses solid state storage, a bunch of those tiny chips, now you have a solid state drive. It accomplishes the same thing for the computer. It's a way you can store information off to the side that you're not using right now, but you may need at a later date, and it'll remember it even without electricity being applied to it. It just remembers. So that's a solid state drive. Two different meanings for solid state.